Hello and welcome back to yet another lecture on this NPTEL course on advanced plasticity of solid continua. We were discussing about the convex functions, but we have to move on and discuss about the convex analytic approach as a whole. So we were discussing in the last talk about the convex function phi, right? So in many cases you will actually come up with convex functions which are everywhere differentiable. Now if it turns out that the convex function is everywhere differentiable, then there is a better way of explaining the convexity using what is called the supporting hyperplanes, right, the concept of supporting hyperplanes. So let us do that now. Okay, so let us take a look at that slide. Gradient as a supporting hyperplane. So basically you can find the gradient of phi, correct? Phi as a function of a vector or tensor x, right? So gradient of phi is available for me because it is smooth. So the gradient defines a hyperplane. This hyperplane, so this is my convex function, right? This is a point on the convex function. This is the supporting hyperplane, right, at that point. Similarly at this point the supporting hyperplane will be this and like that. Okay. So you see this is my this description for the supporting hyperplane. So let us say this is my point x, this point is x, correct, and this point let us say is y, right. So this is phi y and this is phi x. You can clearly see that phi y has to be greater than phi x times the gradient of phi times y minus x, correct. So gradient of phi times y minus x, if you add that to phi of x, then you will be brought from this point to here, okay, which will be below this convex plane, the convex line, right, the line, the curve denoting the convex function phi. So essentially therefore this is the requirement, phi y has to be greater than or equal to phi x plus grad of phi of x dot y minus x, right, for all y, because I can choose y arbitrarily any point y on that convex curve. So this gradient, therefore each such gradient, so this is one such gradient, you can think of each one of these lines as a gradient. This is one gradient, this is another gradient, like that, you understand. So there are so many, right, here there is another, right, a third gradient. Each one of these supporting hyperplanes can be thought of as a gradient because this gradient defines it, all right. So therefore the gradient should define a supporting hyperplane. The function lies above the tangent, as you can clearly see. The unfortunate thing is with this idea, so this is also true. So if phi is a convex function, then this is always true. This inequality which is written at the top of the slide is always true. But unfortunately in many cases we cannot find grad of phi. What should we do then? You know, so we generalize the notion of a gradient for such cases. For example, if there is a corner, for example, what will you do at the corner? You cannot find the gradient, right? So therein the notion of a subgradient or subdifferential comes in and becomes extremely useful. Okay, so we need the generalized notion of a gradient, which is the subdifferential. Let us discuss what the subdifferential is, which is the generalized gradient. Whenever phi is sufficiently smooth and the gradient exists, the subdifferential is the gradient itself. That has to be understood first, okay. So there is no difference, but otherwise in general you can define the subdifferential by taking the cue or the inspiration from this expression. Here this was the gradient, right. So instead of this, think of this as g, grad phi, let us call this as g. But if grad phi does not exist, then also I can write something like this in terms of the supporting hyperplanes. Like for example, think of this, this is my tent function or inverted tent function. This is the point where there is no derivatives possible at the tip, right. So what are the supporting hyperplanes here? If we are away from this lowest point, suppose here the supporting hyperplane is this line itself. Here on the right limb the supporting hyperplane is this limb itself. But at the bottom where there is no differentiability, there are so many supporting hyperplanes. One is this, the other is this, the third one is this, and so on. You see, these are all supporting hyperplanes. So each supporting hyperplane being a possible, subdifferential in this case, right. So there are so many such supporting hyperplanes. So the subdifferential therefore in this case will be a set. Each such subdifferential therefore can be called by a gradient like object G, right, such that this inequality is still satisfied. Phi y has to be greater than equal to phi of x plus G, that is the subdifferential dot y minus x. That dot is an inner product. In case we are talking of tensors, then appropriately it has to be put, okay. So each such G del phi, so all the set of these subdifferentials, all these supporting hyperplanes at a point of no differentiability, they form a set, right. So that set is called the subgradient, okay. So that subgradient or subdifferential is called by the set del phi x, right, del phi x, right. So you can see that all these lines that I drew here, these are basically the lines, the elements of del phi x when x is here, okay, at this lowest point, correct. So therefore this is a very, very useful thing. Let us actually try to understand it in the context of a very specific example. That part of this I have already told you. This fx is modulus of x, right. So fx, this is fx is modulus of x, right. So this is like this. This is all 45 degrees. This is also 45 degree. I am sorry about the slight mismatch of the angles here, but assume that this is also 45 degree, this is also 45 degree, okay. So this is my x and this is x equal to 0 here, all right, at this tip. So when x is greater than 0, then clearly there is only one supporting hyperplane, which is this line, right, this line. So it is basically plus 1, the gradient is plus 1. If it is less than 0, then the gradient is minus 1 this way, okay, plus 0 is this way, gradient is minus 1, plus 1 here, minus 1 here. So these are all singleton sets. These are also subdifferentials because the gradients exist. That does not mean that subdifferential is not valid, because subdifferential is a more general idea. It includes the usual notion of gradient, as I have already said. But at x equal to 0, you have all the possible values from minus 1 to plus 1. You can see that starting from minus 1 here, I can go anywhere. I can go, I can have this line, I can have this line, I can have this line, till I have this plus 1, this line, okay. So therefore minus 1 to plus 1, all the values in between, including the two ends, will be the set of this G, which is the set of this subdifferential for this fx at x equal to 0. This simple example explains why non-smoothness leads to sets of admissible directions, not just one but multiple directions, each one. So think about, I will just come to this important thing a little more with a little more detail. It also shows that the plastic flow at the yield corners, wherever there are corners, the plastic flow will not be unique at the corner, okay. So we will come into the details of this as we move on, but for the time being, this notion of subdifferential, we should look at it as a very, very powerful concept. This here we have essentially the picture, the diagram indicating fx equal to modulus of x, all right, and the subdifferential del fx on the right, okay. You can see that this darkened red vertical line at x equal to 0 taking values from g equal to -1 to +1. Okay, this is +1, this is -1, -1 to +1, all the values in between including -1 and +1 are possible values, okay, for the subdifferential. So this is how it happens, right. You can easily generalize it to higher dimensions, that is the most important thing. Now here, before we move forward, there is an interesting thing that I should tell you. This kind of functions, you know, here I called it as fx, but you should think of it as phi x, okay, phi x equal to modulus of x. Suppose I think of x now as the plastic strain rate, right. Then if you take the the gradient of this, you typically get something like a stress. You should also remember what we did in elasticity using Coleman-Knoll when we did the thermodynamic closure. We got a relationship. Suppose psi is the free energy. In elasticity, free energy means strain energy, right. So basically it is a function of, let us say, small strain epsilon, right. You can see that psi a function of small epsilon, it is the free energy, right. So we saw that sigma is equal to del psi by del epsilon, you remember. This is nothing but a subdifferential, but in this case it is just the standard gradient because we considered psi to be sufficiently smooth. So basically if I take a gradient like this, I got stress, correct. That you have to remember. That means when I take a subdifferential of a function which is a function of the strain rate, plastic strain rate, I should get something like stress, because stress is related to plastic strain rate. Remember the condition for codirectionality hypothesis and flow rule. So that is what you should recall, right. That is a very important point. Now let us talk about an important issue here, which is the most important pivot in understanding this this convex analysis, which is the Legendre-Fenchel transform. Okay. So in plasticity we actually often switch between two conjugate variables. So one is force, the other is flux, like strain rate and stress, right, constraints and reactions, right, and stresses and strain rates and so on, right. So basically if you multiply these two conjugate variables, that is to say if you take the inner product, right, of these two conjugate variables, forces versus fluxes, then you get something like either energy, or in this particular case more appropriately you get power, energy per unit time, okay. So these conjugacy of variables, so we use both of them. We sometimes use stress, the deviatory part of the stress, sometimes we use the strain rate and things like that, right. So the mathematical operation to do this switch in a principled manner is what is called the Legendre-Fenchel transform. Towards that we need to understand what is the dual to a vector space, because it turns out that this conjugacy is very similar to the notion of a duality. That means force is dual to flux, something like that. The strain rate is dual to deviatoric stress, okay. So if V is a vector space or a function space, if you know about it then no problem. Many of you who have gone through a course in linear algebra may know what is the dual to a vector space is. The dual V star is the space of all linear functionals f that acts on V and leads to a real number. Let us give you an example of what this V star could be. Let us take the V to be the vector space of all three dimensional vectors, all real numbers, okay. The elements of the three dimensional vectors are all real numbers and they are all written as column, three dimensional column vectors. Then V star will consist of row vectors. You should think of an element in V star, that is a row vector, as a function on this column vector. How? You just apply the row vector to the column vector through a dot product or matrix multiplication, you get a real number. This is precisely what we said here. So basically we can think of the row vector as a functional, linear functional on V, the original vector space of three dimensional column vectors, to lead to a real number, right. So this is the idea. So therefore the set of all row vectors will form V star here in this particular case. Now let us talk about the Legendre-Fenchel transform, right. For that, let us take a function phi which actually acts on the vector space or function space V and is scalar valued, that it can lead to any real number including plus infinity, but never minus infinity. Okay? Remember that. So, it is a scalar valued function, phi is a scalar valued function of vectors or tensors, whatever. Now, its Legendre-Fenchel dual or Legendre-Fenchel transform is phi star, which is basically a function from V star, the dual to V, to the real number including plus infinity again, and this phi star, the Legendre-Fenchel dual, is given by this expression. This is a very important thing, so pay attention to this aspect, this expression, which is the supremum, that is the maximum over the set V which contains different x's, different x, right. X, you can think of x to be the strain rates, all right, any fluxes, right. So, supremum over all such fluxes x such that you can think of now G to be possible stresses, right. So, such that G acting on x and producing some power like thing minus phi x, the original phi, right, that you have to take the supremum for all such x, right. So, when you take a supremum of this G x minus phi x over all such x, you do not have to differentiate phi x. If phi x is differentiable, then of course you take a derivative, but if it is not, then also this relationship, this definition is valid. Okay, you have to just pick up the maximum, whatever the maximum of the set is. Okay, so therefore no differentiability of phi x is assumed here. Remember that phi in future will be like a dissipation functional, it will be a function of the strain rate, it will basically denote dissipation. Dissipation is a real number, so that is why it is basically a scalar valued function, right. The strain rate is basically a tensor which will be living in V, right. If you take the subdifferential of phi, then it will lead to some stress sigma 0, basically it will basically be living in V star. This is the scenario. Okay. So, phi lives in the rate space, strain rate, typically plastic strain rate. Phi star lives in the force space, deviatoric stresses or stresses if pressure dependent plasticity is concerned. Okay. So, this transformation through the Legendre-Fenchel definition measures how much work a force can extract from a rate, correct, how much power typically a force can extract from a rate. Now, this is a very important thing now, which is called the Fenchel inequality, right. What does it say? It says that for all x in V, that is, think of again strain rates, right, in V, and G in V star, think of stress in V star, we have the inequality. So, stress times strain rate on the left hand side, which is basically some power. If you just take the stress arbitrarily, that must be less than equal to the sum of phi x and phi star G. Phi star, as I told you, is a function of stress like quantities G. Phi is a function of the strain rate like quantity x, right. The sum of it gives the kind of a total energy content associated with both this stress based. You can think of this phi star as the complementary energy, right. You have heard of that, right. So, Gx has to be less than equal to this sum of this phi x plus phi star G. Why is it true? That we will see, but there is an equality associated with it that is most interesting. That means, when is this equality, strict equality, that is Gx equals phi x plus phi star x, when is it valid? It is only valid when and only when you get this G stress as a subdifferential of phi. That means think of the subdifferential as the gradient. So we already know that the gradient of the free energy gives you stress, correct. That is the right stress to ensure equilibrium, correct. So actually when this happens, when G is the subdifferential of phi, then this strict equality is valid. This corresponds to something that we are looking for in plasticity actually, okay. So more than the inequality, the equality is more interesting for us. The inequality is also useful, okay. So now you know, in order to understand why this inequality is true, you can clearly just directly apply to the Legendre-Fenchel formula, transform formula. So phi star G is the supremum of all y in V, all strain rate like quantity in the appropriate space of this, right. Now you know, supremum means the maximum, right. So therefore I can say, if I remove this supremum from here, I can simply say that phi star G has to be greater than equal to Gx minus phi x for all x in V, correct. This is true because this is the maximum possible that you can get with the supremum. Just rewrite this and you get this inequality that we started off. Gx is less than equal to phi x plus phi star G, which is pretty straightforward. But the equality, when G belongs to del phi x, then this equality is valid. That is not that straightforward, but it is still simple enough. We can prove it, but it will take some time. But I will do this anyway for your benefit, right. So the equality has two parts in it. What are the two parts? We said that if and only if, that means if G belongs to del phi x, then this equality is valid. But I can argue it from the converse side, that means if this equality is valid, then G must belong to del phi x. If that if and only if condition has to be met, then both ways I should prove this, okay. So this is exactly what we propose to do now. First, assume the forward logic, that means G belongs to, assume that G belongs to del phi x. By definition of the subdifferential, this means, remember this definition of the subdifferential, then this means that phi y must be greater than equal to phi x plus G y minus x for all y in V, correct. Now you rearrange this, okay. So you take this Gy to the left and leave the rest of the things to on the right. So basically this means that Gy minus phi y, yeah, with a minus sign here, okay. So then this with a minus sign, basically what happens, this greater than equal to becomes less than equal to. So this is trivial, okay. Now this is one inequality that we got, but from phi star G's definition, which is the supremum of Gy minus phi y over all y, we may write that phi star G, correct, must be less, so basically must be less than equal to Gx minus phi x. And why is it so? Because so basically this phi star G you can put so basically phi star G is the supremum of Gy minus phi y, right. So Gy minus phi y comes here, the supremum of it is phi star G, correct. So therefore this inequality is valid for all y, irrespective of whether it is supremum or not. So I can definitely say that phi star G must be less than equal to Gx minus phi x, correct. But then the Fenchel inequality tells you that phi star G plus phi x must be greater than equal to Gx. That means phi star G greater than equal to Gx minus phi x. This is a contradictory statement to this. Do you see that? The only way the both can be true is by requiring that the phi x plus phi star G equal to Gx. So this is one way of proving it, okay, the forward logic. The reverse logic, the converse of it, for that you have to assume that this holds, that is phi x plus phi star G equal to Gx. Then show that if this is true, then G must be in the set of subdifferentials of phi. Okay. To do that, you again invoke the definition of the subdifferential phi star G, which I have just written here, right. This simply means that because both of these are true, correct. So basically this together means that phi x from here, right, plus phi star G I have put here, okay. Phi star G, instead of the supremum I have put Gy minus phi y. So Gy minus phi y, if I put, then it must be less than equal to the supremum, right. So therefore this is true, correct. This must be less than equal to Gx, you understand. Now you rearrange this, you get this, correct. But if you rearrange this statement and get this, you immediately see that phi y greater than equal to phi x plus G times y minus x is the definition of the subdifferential, where G is the subdifferential of phi x, right, for all y. So that means G belongs to del phi x, correct. So we have proved it also. So you see, this is a very important thing, that the equality phi x plus phi star G equals Gx occurs only when G is a subdifferential of phi. Another thing we need to construct the function phi in our context would be the notion of Euler homogeneous functions. You will see later on that I will be talking of the fact that phi, which is basically the dissipation potential, right, in the rate independent case, will be Euler homogeneous of degree 1 okay. So let us define what is an Euler homogeneous function. A function f x1 x2 etc. is called homogeneous of degree k if f of t is a scalar multiplier, not time, okay, any scalar multiplier, positive, for any positive scalar, f of tx1 tx2 etc. is equal to t to the power k of f x1 x2 etc. okay. So if this is true, then we say that the function f is Euler homogeneous of degree k, For such a thing, it is very easy to show, it is called the Euler's theorem, that the functions, the increment in terms of away from 0, in terms of this quantity, the function's increment away from 0 is nothing but this is the increment in the x1 direction, x2 direction and so on, right, multiplied by the derivatives. That gives you the increment in each direction and you just sum them up. That is nothing but equal to k times f. So you can write the increment in terms of the function itself, provided you know the degree of homogeneity of the function. Okay, so to do that, you can just differentiate this defining equality for the Euler homogeneous function, differentiate it with respect to t. Okay, you need to use the chain rule, and then finally set t equal to 1. So this is a very simple thing, so I am not going into the details. So you can actually show that, right. So now we come to our situation, because the homogeneity of degree 1 is of great importance to us, right. So now, for example, the 10th function will be coming again and again. Why does it come again and again? I will actually try and explain to you. Before actually getting into the degree 1 homogeneous function, let us consider one such function. Okay, so for example, phi x is modulus of x is basically degree 1 homogeneous. Why? You can just see phi of lambda x, lambda will come out for positive lambda. So basically it is k is basically 1. So this is Euler homogeneous of degree 1. Now the function looks like this, correct? This is my axis, right? This is my x and y axis, right? The function looks like this, correct? The thing is, this is my phi x, this is my x, correct? The thing is, at the minimum here, at the tip, you have so many different values for the subdifferential. Each one of these, because these are subdifferentials, say supporting hyperplanes, these. What are the possible values? -1 to +1, correct. Now think of the set of all stresses that are admissible in plasticity, in perfect plasticity, minus sigma y to plus sigma y being the yield stress. Suppose sigma y is 1, the stress is nothing but the derivative of phi x, subdifferential of phi x. So when I actually minimize this and go to x equal to 0, I get all possible values of admissible stresses, -1 to +1, I mean provided sigma y is equal to 1, otherwise I have to change the function. You understand how this non-uniqueness of the subdifferential at x equal to 0 plays a very important role in defining the zone of admissible stresses or the elastic region. This is how basically the elastic region comes, through the notion of subdifferential. Okay? So basically we will see therefore more clearly that phi x in such cases will define one form of energy, power, corresponding to the plastic strain rate. Phi star in this case, if you take the Legendre-Fenchel dual, phi star in this case will take up the form of the dual power corresponding to the stress based description, right. Both are power like object, both are energy, right. And you must also therefore understand that the sum of them therefore gives the total power landscape for the plasticity problem in the rate independent case, correct. This is the basic idea here, and we will observe a very important thing, two important things. One is that actually when phi x is a degree 1 homogeneous function, then always phi 0 equal to 0. At x equal to 0, phi 0 is always 0. Why? Because you can observe that phi 0 is phi of 0 times x, but 0 is the multiplier lambda, right. So 0 comes out because it is degree 1 homogeneous. So it is 0 times phi x, which is 0. So it is always true that phi 0 equal to 0, right. Now phi star in this case, we will prove it in the next class perhaps, that phi star in this case is basically an indicator function which will be 0 in the admissible set of stresses, in this case -1 to +1 in this particular problem where phi x equal to modulus of x, but otherwise it will be minus sigma y to plus sigma y or appropriately, and phi star will become infinity outside. That means it will act like a wall about the region of the elastic stresses. That wall will be impossible to break through. That is what actually imposes the constraint of plasticity, the fact that phi star is an infinite energy outside the zone of admissible stresses. So you see how interesting it becomes provided you understand how to calculate phi star for this degree 1 homogeneous case. Actually in the next lecture we will see that for this degree 1 homogeneous function, right, the phi star we will be automatically getting an yield set from minus sigma y to plus sigma y, or -1 to +1 in this case, right. So you differentiate the differentiate phi, or take the subdifferential of phi, you get information about stresses, remember that, right. So basically this is what the introduction to the concept of convex analysis tells you, that it offers you an energy based perspective whose minimization, if you put it properly, pose it properly, you minimize that energy and get your solution for plasticity. That is a much more powerful rule than doing the kind of things that we have seen that classical plasticians typically do, right. So we will basically prove these things, the nature of phi star, the expressions for phi star in the next class for degree 1 homogeneous functions. So we will also come back to what we discussed today, but my suggestion to you again will be to go through this talk and the one preceding it again and again till you fully understand what I have discussed fully. The first time you will probably understand only 25-30%. The second time if you go through it again and again, you will see that your understanding improves, right. So, so all the best in your effort to try and understand this, because this will be very useful in our next lecture. Okay. Thank you very much, and I will see you back.